So, good afternoon, everyone present here. So, myself, Aditya Vijwani from the Albag Educational Institute, Agra. And my talk for this VSSP 2024 will be subspaces of R, R2, and R3 over R. Like my field will be real numbers. So, I'll be talking about what are the subspaces of R, R2, and R3, and we'll also be proving that they will be the only subspaces of R, R2, and R3. And also in this talk, we'll be looking it more like a geometrical way at many points. So let us start with the subspaces of R. So while starting, let me know if you know any of the subspaces of R. Yeah, so do you know any subspaces of R?
Zero.
Yeah. So yeah, zero vector is a subspace and R is also a subspace of R, like the whole of real line. So are there any other subspaces of R other than zero vector in R? Yeah, so there are no other subspaces other than 0 and R. But how do we prove this? So to start with, let us take W to be a subspace of R. Now, what is the relation between W and R? I've taken W to be my subspace of R. So what's the relation between W and R? Yeah, so since W is a subspace of R, W will be a subset of R, right? So now if W is equal to 0 vector, then we are done, right? So why can I say that if W equals to 0 vector, then we are okay with it? Because since I took W to be my subspace and it's just 0 vector and it will also be a subspace, right? Trivial subspace, I can say. So it is okay. But if W is not equal to 0 vector, then what can I say about it? Remember, W is a subspace of R. Okay. So if W is not equal to 0 vector, then what can I say about W? What elements will be in W? So W will contain any non-zero vector. So let me name it as V. Now what do you know about V? As we already know that W is subspace of R. Okay. It contains a non-zero vector V. So what can I tell about V? What is V like?
Some since subspace of R, it should be some real number.
Yeah. So since I took V to be a V is my non-zero vector and it is a real number, right? So now, can you show that 1 belongs to W? Can we show that 1 belongs to W? Remember, I have taken V to be my non-zero vector. Now, can we show that 1 belongs to W, which is a subspace, W is a subspace, right?
Yes,
Yeah, how?
we can take the inverse of multiplicative inverse.
Okay, yeah, I get
One
it.
upon V. One upon
Yeah,
V.
yeah. So basically, we can write 1 as 1 upon V multiplied by V, which gives me 1. So see, this 1 upon V is defined only because I say that V is the non-zero vector. So now let X belongs to R. Okay. Then X can also be represented as X into 1. Right. See, I already showed 1 belongs to W and I say X belongs to R. So I'm representing X as X into 1. So it will also belong to W. So we say that R is a subset of W because I showed that an element of R is also an element of W. So we are done. So why does it suffice to say that R is a subset of W? So we are done. What have I actually proved? I just showed that an element of R is also an element of W. And remember, I already took that W is a subspace of R. Yeah. So basically, we have proved that both are subsets of each other, right? R is a subset of W and W is a subset of R. So W will be whole of R. Hence, I say that the subspaces of R will be 0 vector and R. So this was an easier one to start with for subspaces of R. So we now come to subspaces of R2, which is kind of center to this talk, and we'll see many aspects geometrically and theoretically in that. So again, I start by asking you, do you know any subspaces of R2?
R,
What?
0, R, and R2 itself.
Okay. Okay, so there's a thing like, okay, you're partially correct. Like it's zero vector, all the lines passing through origin and R2. Yeah. So now to prove this, we'll again start in the similar manner. Let W be a subspace of R2. Then again, we say that if W equals to zero vector, then we are okay. Why can I say that? Because I took W to be a subspace of R2 and it's just zero vector and it is a subspace. So we are done. If not, if W is not equal to zero vector, then what can I say? What will W contain? See on the similar lines what we did in subspaces of R.
All its scalar multiples.
Scalar multiples of what?
That vector v. So we'll get a line.
Yeah. So basically here that vector V will look like this, right? AB. So to put it correctly, I say that W contains a non-zero vector, non-zero, and I name it as AB. So it will look like this. So earlier it was just a real number. Now it belongs to R2. So now let's take a line which passes through AB and 0, 0. So basically, you're taking a line on our plane R2 such that it passes through AB and origin. So I can also say that all multiples of AB will also lie on this line. Right. So all the multiples of AB will also lie on this line joining AB and 0, 0. So can we see that this line is subspace of R2?
Yes.
Yeah. How?
Because if we add any 2 points on this line, it is also going to be on that same line.
Yeah. And
And they are all scalar multiple. Any scalar multiple of a point will also be on this line. So it's a
yeah.
subspace.
Yeah, so it satisfies my properties of subspace as we discussed here, like any 2 points on this line. So their sum will also be there on the line itself. And all the multiples of AB will also lie on this line that we already discussed. So it is also a subspace of this line is a subspace of R2. So I write it in a set notation form as this. Uh, if W equals to alpha times AB, where alpha belongs to R, alpha is my scalar. So we are done. We just saw that it's a subspace, right? Now, if W is not equal to this set alpha times AB, then it means that W contains a non-zero vector CD, which is not in this set. So to explain this, let me show you uh, the plane. So basically what we just saw is this line is basically the set alpha times AB, where alpha belongs to R, right? Now I say that if W is not equal to this set containing all the points on this line, then it will contain some another point which I named as CD, right? Yeah. So which I named as CD, which will not be in this line, right? So now CD is again again we take a line which passes through CD and origin. Okay, and we also see that all the scalar multiples of CD will belong to W. That is, the line joining 0 0 and CD will be contained in W. So we are saying this on a very similar basis how we did for AB. So for AB, like we just discussed, it will be a subspace. For the line joining AB and 0 0, it will be a subspace, right? So for similarly for CD also, it belongs to W. It's a subspace. So combining them, let me write a set, say alpha times AB plus beta times CD. So we already saw about lines passing through origin. We can actually generalize that for any line. So CD and AB are just general points, right? So it can happen for any line passing through origin. But what if I take linear combination of 2 points which are not on the same lines? So understand this, that the points on the line joining AB and origin will not lie on the points will not be the same as the points on the line joining CD and origin. So I have this set alpha times AB plus beta times CD, but let's look at it geometrically. So if beta equals to 0, beta CD is basically all the scalar multiples of CD. So beta is my scalar. So if beta equals to 0, can you tell what this set represents? If beta will be 0, then it becomes alpha times AB. What does this set represents then if beta is equal to 0?
Again, the subset of W of AB just does that line.
Yeah,
If
so
beta is 0.
this blue line, right?
Yeah.
Yeah. So basically, beta is 0. I get this line. So basically, all the scalar multiples of AB will all be there in the set. Now, just see, if beta is equal to 1, then what I'll get is, I'll get any point on this blue line plus CD. So basically, the points on this line will be shifted by CD, all the points, right? So I get a line almost like parallel to AB such that the points are shifted by CD. Similarly, you see that if I take beta is 2, then the points on this blue line get shifted by 2 times CD. And like this, if I keep on going, if you see my cursor, I'll get like parallel lines like this. And since my beta can be negative, then I can get lines below it also, right? And in the similar manner, can you tell me if alpha is 0, what this set represents? If alpha will be 0, then this set represents this green line, right? Joining CD and origin. In a similar manner, what we did for this line joining AB and origin. So again, we can get lines parallel to this line joining CD and origin shifted by the factors of AB, like alpha times AB. So alpha can be anything. So do we get a feeling that this set represents the whole of R2? Because see, changing beta and alpha, I'm getting lines almost anywhere on R2, right? It's just a matter of shifting the points of any of the line by some factor of AB or CD, whatever you choose alpha or beta to be. So yeah, that will be a subset of W. So now we get a feeling that the linear combination of AB and CD should span the whole of R2. So to prove that, I take an arbitrary vector in R2, say xy, and my claim is xy can be expressed as alpha times AB plus beta times CD. Basically, they're linear combinations. So since AB and CD are linearly independent and form a basis, for R2 what we need? We just need two vectors which are linearly independent to form a basis. So their linear combination will span R2. Right. So from here also we can say that, yeah, I can get any vector x, y and R2, which is formed by the linear combination of AB and CD. But an alternative way to look at it can be, If I solve this, I'll get an equation which can be written as beta equals AD minus BC upon AY minus BX. If you will just open and solve this, you'll get this. So here, what can you say? What should be the condition for beta to exist basically? Can you say what should be the condition for beta to exist? So basically, for beta to exist, AY minus BX should be non-zero, right? So that this denominator should not go to 0. And if AY minus BX is non-zero, then it's okay. I'll get my beta. But what if it is 0? See, if AY minus BX is 0, then I get this equation as AD minus BC equals 0 times beta. That is AD minus BC equals 0. Now, this implies that I can write CD. This implies that CD will lie on the line joining A and B. And that line I can represent by x upon A equals to y upon B since it passes through origin. But since I can, from here I can write C in terms of A and D in terms of B. So basically what I'm doing is I'm writing C comma D as as a multiple of AB only, right? But what I started with CD to be a point not on the line joining AB and origin. So that cannot happen. So obviously these 2 points have to span the whole of R2. Basically their linear combination should span R2. So we get a subspace, the whole of R2. So let's pause, review and proceed. Wait for a few seconds and recall what we went through. We started with subspace of R2. We started with subspace of R. Then what we did, recall, we took W to be a subspace. Then we proved for zero vector. Recall how. Then we showed that the whole of R is a subset of W. Right? How? We took a point in X and X can be represented as X into 1. So by this we showed subspaces of R. Now then we went through subspaces of R2. Similarly, we showed zero vector there, right? Then we took a point, then we took a line joining a point AB and origin, and we showed it was a subspace. Recall how? And then we got a set which was a linear combination of basically any 2 points on the line joining AB and origin and CD and origin. So their linear combination spanned the whole of R2. So similarly, we go to subspace of R3, which should be very easy on a similar basis. So again, can you tell me the subspace of R3? Any subspaces you know?
Zero once again.
Yeah. So 0 will be one of them, and lines passing through origin, planes passing through origin, and the whole of R3. They'll be the subspaces of R3. So to start with, again I took the same W to be a subspace of R3, and if W is equal to 0 vector, then we are happy. So basically it's the trivial subspace. So we discussed it twice. Now if W is not equal to 0 vector, then it will contain a non-zero vector. Similarly what we have been doing. Now I take this vector as A equals to A1, A2, A3. This is my non-zero vector. So W will also contain the line passing through A1, A2, A3 and origin. Similarly, similar to R2, what we did in R2, we saw a line joining AB and 0, 0. So here W will contain a line joining A1, A2, A3 and origin. And if W is this line only, then we are done because it will be a subspace. Follows all the properties of subspace, right? Yeah. So what will be the equation of this line? This line passing through A1, A2, A3 and origin. Can you say? So I can write it as x upon A1 equals x upon A2 equals z upon A3. And simplifying, I get these two equations. So do these equations make you familiar with some equation of some form, like representing something geometrically? Can you recall? So they basically look like, yeah.
Plane.
Yeah, plane with one of the coefficients of z, here z is 0.
So then
Coefficient
XY.
of z is 0, and here the coefficient of x is 0. So yeah, seems to be some special case of equations of plane. Yeah. So now, if W is not equal to alpha times A1, A2, A3, basically, if W is not equal to this set, then it will contain a point B1, B2, B3, which will not be in this set, right? So this means that B1, B2, B3 will not be on that line joining A1, A2, A3 and origin, but it will be in the same plane, but not on that same line uh, on which A1, A2, A3 was. And similarly, if W is this line, it will be a subspace and we are done. So again, if I consider the set alpha A plus beta B, remember here A is A1, A2, A3, B is B1, B2, B3. So it will be a subset of W. Will it be? Yeah, so it will be a subset
Yes.
of
Yes.
yes, yes. So it will be a subset of W. We just uh, saw this notation in R2 also, how it spanned the plane. So it is a subspace and it is a subset of W. So geometrically, you can see here how this is the line B1, B2, B3 and joining origin and B1, B2, B3, and yellow line represents joining origin and A1, A2, A3. Yeah. So now the equations of the line basically passing through origin in terms of plane, I wrote them as A1 plus B2 plus C A3, and similarly AB1 plus BB2 plus CB3. So these two equations will have a non-trivial solution which satisfies them. Why can I say that these two equations have a non-trivial solution? Because there are two equations in three variables. So there was a theorem, right? M equation in n equation in n variables. Then we had cases m greater than n, m less than n. So here two equations in three variables, right? So there it has a non-trivial solution. So does the solution belong to the set alpha A plus beta B? Will it belong to this set?
Yes.
Yeah, it will belong, because see what we did was these points were taken from here only, na? This see this picture. So of course it will belong to that set of alpha A, means multiples of A and multiples of B. So now can we say how to proceed? We have planes passing through origin. We saw lines passing through origin. We saw zero vector. Now can we say how to proceed?
Take another point
Yeah, so
outside the
basically,
plane.
another non-zero vector C I took, which is not in the set alpha A plus beta B, say C1, C2, C3, and it also does not passes on the plane passing through origin. Okay, so to see this, let's see this picture. So basically, I took a point C somewhere in R3 such that it is not on this blue plane. So this blue plane is basically passing through origin, right? It will contain my points, that those lines, you remember, lines joining A and 0, B and 0, and similarly other lines which may be there passing through origin. But I took my vector C such that it does not lie on this plane. So can we say that if I take any C vector not on this plane passing through origin, and A and B, which were already defined earlier, then those three can span R3? Do you have a feeling? See, similarly, changing alpha, beta, and gamma will be the scalar multiples of C. So, similarly, changing the scalar multiples, I can get planes parallel to this, right? Sorry, lines parallel to the lines, as we saw in case of R2. So that was spanning the whole of R2. So here, if I take a vector C, which is not on this blue plane joining the passing through origin, then we have a feeling that it spans R3. And rightly so, since so my claim will be that I take any vector xyz in R3 and it can be expressed as the linear combination of three vectors a1 a2 a3 b1 b2 b3 and c1 c2 c3, where alpha beta gamma are from real line. So since a1 a2 a3 b1 b2 b3 and c1 c2 c3 form a basis of R3, why do they form a basis?
Because it spans R3 and it is linearly independent.
Yeah, it's linearly independent. We took them not to be the scalar multiples of each other. So
Right.
the linear combination spans R3. So we are happy with it. So we saw origin, lines passing through origin, planes passing through origin, and in the last spanning of all of R3 as the subspaces of R3. Thank you.